Hi, everyone. I'm Jeff, and here I have Shashi Gowda and Josh Day with me. Good to see all of you. So out of curiosity, how many people have heard of Julia? Okay, great. How many people have at least tried Julia? Okay, a few people. That's good. So just as a very quick review, so I'm going to talk a bit about just a very high level why we created the language Julia, and then we're mostly going to talk about this new project, JuliaDB. So we had this blog post about addressing the all-important question of why we might need another language. You can check that out if you want more details. But basically, we created Julia to address what we call the two-language problem, where you essentially need different languages for prototyping and productivity versus deployment and performance. And you see this nowadays in that many R and Python packages are actually written in C and C++, and because you need that to get performance. So we saw this as a problem, and we said, you know what, we want one language that can do all of this. And so we designed Julia to be able to do that. So the dream is to be at least as nice as the productivity languages, Python, R, MATLAB, but as fast as C and Fortran. And we did this in kind of a, what I consider kind of a principled way, by not just sort of taking the same thing and just kind of trying to speed it up, but rethinking the design from the beginning in a way that would just naturally lead to a nicer architecture and naturally lead to performance. And there's going to be a tutorial about it, giving an intro to the language on Thursday, and you can find out a bit about how to use it and how it works. So basically, we have a JIT compiler. The paradigm of the language is multiple dispatch. So you can overload functions on all the arguments instead of just the receiver or just the first argument. And there is a type system that can be useful for adding expressiveness to programs. There's a lot of support for metaprogramming, for generating code, which is often needed for performance and for certain hard problems. We have been very into parallelism from the beginning. We've had a distributed memory parallelism module in the standard library from the beginning. And when you put all of these things together, I think actually very interesting things become possible. And in particular, with the combination of features that we had and the abilities to have both the easy language and the fast language in the same package, this turns out to be, I think, a really interesting language to write a database in. And one of the reasons is that with the expressive types that Julia has, they turn out to be useful for describing essentially schemas. And then you feed that into our compiler, and you kind of automatically get optimized code for various different queries and combinations of data types. And so we realized we could use this to make an interesting data system. And so we've recently released this as open source, and it's called JuliaDB. And these guys are going to tell you a bit more about it.
All right. I'm just going to go with this guy. Thanks. All right. So introducing JuliaDB here. So the first question is, like, why do we want this to exist? What are we making? And so the idea is that, like, we shouldn't have to glue together existing tools, like, to get performance. So kind of why, like Jeff talked about, Julia was being designed from scratch instead of just, like, building off of Python. We're kind of building something new as opposed to trying to glue things together. So on GitHub, if you go to various projects repos, there's this little bar that you can click, and it shows the percentage of files that are associated with certain languages. So here is pandas, and you can see it's a big chunk of that is Python. And it's hard to say what percentage of that is actually Python. There's some HTML, some C. We can look at dplyr for R, and so that is 57% R with a big chunk of C++. Another big R package is data table, which adds a lot of features to R's built-in data frames. So that's actually more C than it is R. And then compare that finally with what we have in JuliaDB, which is just 100% Julia. So yeah, everything in JuliaDB, we're not tacking things together. We're kind of building it from scratch and just taking advantage of the type system and the JIT to get specialized code. So the goals here are to bring the promise of Julia to data science. So we're trying to solve this two-language problem, and we want to be able to efficiently work with persistent data sets that are stored in multiple files. We want queries and user-defined functions to be fast. So again, we're leveraging the JIT so that our user functions are just as fast as the stuff that's built in. And we also want JuliaDB to perform the heavy lifting of distributed computing. So if I flip the switch and say add more processes, JuliaDB should be able to take care of that and speed things up for me without me doing a lot of manual work. And then another kind of philosophy behind this is that batteries are included. So we have tools for analytics and just tools for working with data. So as a quick example of just loading data here, since we're in New York, so I looked at this New York city taxi cab data. So this is just looking at yellow cabs, and I'm looking at the first 4 months of data for 2017. So these 4 CSV files make out about 3.2 gigs, 1 file per month. And if I just look at the head of these files, so I think it's 17 columns, and I'm going to set indexes by the first 2 things, so vendor ID and the pickup time. So it gives the pickup time, the drop-off time, and the fare and the tip for every ride in the first couple months of this year. So with JuliaDB, I just need to really load this data, kind of ingest it once. So if I call add procs in Julia, it's automatically going to add as many processes as I have cores available. And then I'm going to use JuliaDB. I'm going to set the path to my data. And then when I call this load table function, it's going to load or attempt to load every single CSV file that's in that directory. And I'm setting the columns that I want to index by as the first 2 things. Now I can save this for later usage. So once I save this database as my data, I can start a new Julia session, and when I go to load this, it's just nearly instantaneous. So we're looking at a data set, and so here's about 40 million observations, and it's running on 4 processors at the moment. We can see, so Julia automatically gets this type information from all the columns, and I hardly did any manual work to this, and JuliaDB just takes care of a lot of that. So now we have our data loaded, so we want to be able to do things with it. So I'm the author of this package called Online Stats. And the idea is that it uses online algorithms, so nothing to do with the internet, but it's that its input gets entered piece by piece. So each statistic or model inside this package is its own type, and everything gets updated 1 observation at a time. And so online stats is part of this batteries included philosophy. So you can automatically do a bunch of different summary statistics like means and covariance matrices and approximate quantiles, things like density estimation with histograms. You can do things like regression in a closed form, so you can get exact regression estimates, even if you're estimating it online. And then you can also do approximate penalized generalized linear models. So there's a variety of different algorithms and losses and penalties that you can plug in, and all this stuff gets compiled really well just because Julia is depending on the JIT and multiple dispatch to do all these things. So there's a couple unique features of online stats that I haven't seen anywhere else. And so one of these things is just the ability to plug in different weighting types. So mean is a type in online stats, and you can plug in different ways to weight this thing. So an exponentially weighted mean gives every single observation just a constant value. So if I give everything a weight of 0.1, so this red line here is an exponentially weighted mean. So if this is parameter drift, or depending on who you ask, that's called non-stationarity or concept drift. So if our true model is changing over time, an equally weighted mean won't be able to capture that, and exponentially weighted mean will be able to. So this is a very simple case, but this will also happen with linear regression and more complicated models. So you can also adapt to your data. And then also calculations can be done in parallel. So just like I said, in JuliaDB, I want to be able to just flip the switch, and it's going to do things distributed for me. And essentially, it's able to do that with online stats, because online stats can do things like embarrassingly parallel. So if I have some statistic that I give these 3 values, another one I give these 3 values, another one these 3 green ones, I can merge them all at the end, and that's just exactly equivalent to giving one of these statistics all these observations in a row. So essentially, JuliaDB knows how to manage this. So again, when you flip that switch to say do this distributed, it knows how to run things through and how many stats to make, and then how to merge them at the end so that the user actually doesn't see any of this going on. All right, so here I'm just loading the plots library in Julia and online stats, and I'm going to produce images with Plotly just so that they're interactive. So one of the main operations in JuliaDB is this reduce. So I can give it any Julia function, so that plus is just a normal function in Julia. If I want to calculate a mean, say I want to select fare amount from this thing and divide it by its length, so the average fare is $12.70. So again, mean is a type in online stat. I can also reduce by this mean type, and it's going to spit out that value for me. So a little bit more interesting things. So say I want to look at just the distribution of the number of passengers in this first couple months. So fit categorical is a type in online stats where it essentially holds a dictionary of each level, and it also is going to add in the count of each thing that we see. So I'm selecting passenger count, and I know that that column is an int64, so I'm telling fit categorical that's what it is, and this runs through. So again, we're looking at like 40 million observations, so this runs through fairly quick, and we can get that categorical distribution of the number of passengers. If we want to look at things like continuous variables, so histograms are common types for that. So here I want to look at two columns. So I'm going to select the fare amount and the tip amount from this database, and I'm giving it two histogram objects, and that's because I'm looking at two different things, and then I can plot these at the end. So I was actually a little bit curious about why there's this bump here at the end, but so maybe some of you experienced this. There's a fixed price if you take a taxi from JFK to anywhere in Manhattan, which is $52. So that's why there's the spike right there. Yeah. And now I'm going to hand it off to Shashi.
Hi, so benchmarks. How does JuliaDB perform compared to, so we basically benchmarked against pandas. So in this plot, we are plotting the performance relative to pandas. So 1 is basically the speed of pandas. So if any point is below that, that means it's faster. These benchmarks are faster. If any point is above that, that means that it's slower. So some of these points are below 1, like I think most of them. So we have fast joins, and then loading CSV is pretty fast, and then just doing aggregates is pretty fast. And there are a few things that we are working on which are not yet there, but things are within 2 or 3 times the performance of pandas. So yeah, so more detail about the performance. Sure.
On the previous slide,
sure.
Where you have 2, is it 2 times slower, or is it?
Yeah, it took twice as much time. Yeah. So yeah, more numbers. So reading CSV, we worked on this quite a bit to make it fast, and we can get pretty good speed on this data set, New York taxi data set. So I was trying this out, and I realized that pandas is reading dates as strings. So I also benchmarked that in Julia, and it turns out reading dates as strings is actually slower because it keeps allocating the string, while in pandas it takes longer. It's faster actually. So that is just to show that date time parsing is pretty fast in Julia as well. So group by benchmarks. So there's one benchmark where it's like twice as slow compared to pandas. This is because, so this is basically counting the, aggregating the count of number of observations by day of week, comma, passenger count, and the floor of trip distance. Sorry, yeah.
How many cores are you using Julia? Pandas is single thread.
Yeah, so in this benchmark, it's all a single thread. Yeah. So this floor function actually returns a float. So we don't switch to the O of n sorting at that point because we consider floats as continuous variables. But if I did floor of int, then the performance is kind of comparable to pandas. So most of these things are comparable. So these are joint benchmarks. So JuliaDB performs comparable to pandas, but in one case where we're using string keys, 2 string keys, it's a bit slower. I think pandas might be doing some kind of interning or pooled arrays type of stuff. I think we can also get this to be fast. So a bit about the benchmark. It has 80,000 keys, out of which 8,000 keys are unique. And then on the left side and on the right side, there are 8,000 keys, out of which 6,000 of them are present on the left table. So it's like a many-to-one join. So we have two types of tables, one with strings as the keys and one with floating points as the keys. Yeah, so this benchmark was actually done by Wes McKinney. I took it from his blog and then repeated it in Julia. So a bit more about this. This is, so far I've spoken about the benchmarks. I'll be talking about the API, right? API now. So we have two data structures. One is a table, which is like a collection of rows. We treat it as a collection of rows, and you can have it ordered by some of the fields. This is good for like data science workloads. And there is another type called ND-sparse. It stands for n-dimensional sparse array, which behaves more like an n-dimensional array. And it's good for like more scientific kind of workload where the data is regular, like signal processing and stuff like that. So these are the functions we have in JuliaDB, and they all work on both the table and ND-sparse structure, both in distributed and in serial. So you have the usual suspects: select, map, filter, drop array, columns, rows, and then some functions for manipulating columns, and then group reduce, group by, flatten, and then we have join, group join, as of join, and merge. Merge is basically concatenation, and then we have save and load functions which can save tables basically, or any data set. So there are some functions which are specific to the data structure. So first one is load table, which just loads the table, and the second one, the ones which are specific to ND-sparse are here. So ND-sparse behaves like a key-value pair, so you can get the keys, select the keys, and then it also behaves like an array, which I'll get into right now. So the focus in the API is more on having reusable conventions rather than having a ton of options in each function. So an example is the select operation. So in this slide, what you're seeing is this is the code that gets run. This is the code that gets run, and this is the output of the code. And this is the table. The TBL variable is this table. So saying select TBL X will return a vector, which is that column. And then saying a tuple of column names will return a new table with only those columns. And then saying this column name and giving it a function will apply the function to each element of that. And then saying this, which says select these two fields and then apply this function on those two fields. So it's calculating the hypot, which is like the hypotenuse of x and y. So that will give you a vector where each element is transformed this way. And giving it a vector just returns the vector, and it has to be the same length as the table. And finally, you can give it like a custom column, so it gives back a table with that custom column. And then there's more. You can combine any of these in the tuples to get like more complicated things to work. So this is the select operation. Now, you can actually use these selectors in all of these operations, so including map, reduce, filter, group by, group reduce, and so on. So to select any custom part of your data to work with. So for example, in join, you can say, I want to, or say in group reduce, you can say, I want to group by the day of week of a certain date time column, and it will just work. So that's how we've made the API. So a bit more about the ND-sparse structure. So far I spoke about the table data structure, but ND-sparse is more like an n-dimensional array, but the indexes are not integers. There can be any arbitrary data types which can be ordered. So in this case, I'm loading a data set of currency pairs and their bid and ask values at in 2016 December. So I'm loading 5 files, 6 million observations. So here you can see there's a vertical line here. Everything to the left of it, left of the line, consists the index. So this data is indexed by AUD JPY and then the time. And then on the right is the data. So if we can look more into it. So X is my index table. So if you say key type, it'll tell you the key, it's keyed by string and datetime. And if you see the L type, which is the element type, it'll tell you it's a name tuple of bid and ask values. So you can index into this using the values itself. So you can say, give me the data for AUD/JPY at this time point. So it'll give you that. It returns a name tuple. So, but you can also convert this into a table, a relational table. And if you see the L type of that, it includes the pair and time fields as well, because it just iterates by rows. So if you index into the first row, you'll get the first row, rather than just the thing on the right side. So you can also do like range selection. So you can say, give me all the values for these dates. So this is an interval. These dates for all the currency pairs. Or you can say, you can restrict the currency pairs. You can say only Australian dollars to USD and CAD to JPY for these dates. So it'll give you that slice of the data. You know what that is. Okay. And you can, so an index, an ND sparse is most useful when you have, so if you see the L type of this, it says 2 field name tuples. So the name tuples are bid and ask, has bid and ask fields, but it's, an ND sparse is most useful when you just have, you know, a plain type, like a float 64. So in this case, I'm taking out a bid column into a new ND sparse. So I get this. So if I index into that, if I see the L type of that, it's just a floating point. Now I can use array operations on it, like reduceDim, which is like a generic function in Julia for all arrays. You can say drop the second dimension, which is the date, and then aggregate the result by plus. So it's going to add up all the values in the bits for every currency pair we have. So you can also convert a dimension by saying, okay, convert the time dimension by truncating it to the hour, nearest hour, and then aggregate any values in the same hour by doing a max operation. So it's getting the maximum for every hour, and then you have this new index table like this, ND sparse like this. So here I'm taking out the hourly data for only AUD/JPY pair. Now, what I can do with this is I can do a broadcast kind of operation. So if you wanted to divide all the data points using this data point for AUD/JPY for that hour, you can just do ./AUD/JPY, and it kind of does a broadcast for each currency pair. So you can see that if here we have only once. That is because it's dividing it by itself. But for the others, it's dividing it by the $yen value. So this is called a broadcast in Julia, and it's not some special thing. You can give it any user-defined function. You can say broadcast. Instead of divided by, I'm saying hypot here. So find the hypotenuse, like the distance between those two. So it can do that as well. So in summary, an ND sparse is indexed by any arbitrary keys. In this case, we saw like a time series example. And you can index it by intervals of values, iterates by values, behaves like multidimensional arrays, and supports array syntax like broadcast, reduceDim, map, reduce, and stuff. This is great for representing any type of series, especially time series. Yeah, so this is what we have planned next for JuliaDB. So we are working on feature extraction for machine learning and kind of batched machine learning algorithms. So that's coming through. And we want to have more comprehensive out-of-code support. Like right now, you can do online stats out of core, which means that you can have more data than that fits in your RAM, and it'll just handle that. And we are working on having dense n-dimensional data store. For example, you may have satellite imagery, where it's basically indexed by X, Y, Z coordinates, and then over time. And it may have RGB channels, so you want to be able to work with that of that kind of data set. And then we want to work on streaming updates, so something like a streaming data frame, which will work very well with online stats. So, so that's the end of the talk. Thanks, everyone. These are our email addresses. If you have any questions, please do email us. And then you can go to juliadb.org for the website. Thanks. Yeah, sure.
You guys have time for questions?
Yeah.
I think so, yeah.
We have 10 minutes.
Yeah.
When you all talk about the built-in parallelization, we're really talking multi-threaded, single machine, as opposed to...
So Julia actually has both now.
Okay.
So the distributed has kind of always been there, and we have, now increasingly, we have threading support as well. So it does both.
So when we think about that behind the DB, does that mean that you parallelize across multiple machines for storage as well as CPU, or just you can use multiple CPUs? What's the right middle model?
So overall, at the outer level, it's like a multi-process model, because in general. Oh yeah. So at the outer level, it's more of a multi-processing model, because in general you will have really big data sets, and so people want to scale onto multiple machines. So that's mostly what it is. If you have like a single machine with a lot of processors and a lot of memory, it can also work on that by just doing essentially the same thing within that box.
And the intent here is, in the same way that that Pandas is a framework for use within Python, this is a database for use within Julia, as opposed to something written in Julia that we're connecting to with clients of different languages. Is that the right middle model?
That's right. Yeah. So right now it uses what you might call like a peer kind of API, where you're programming directly to the system, the query language and the programming language, and the database code itself is sort of one single system that you're working with. In the future, any database can do client server, right? Because you can, whatever you're typing at the prompt, you might as well just send over the wire and send back the results. So we don't have that style of API yet, but I imagine we will need it at some point in the future, and we'll add a client server mode at some point probably, but we don't have it yet.
Any other questions?
So is a DB a in-memory DB, or is it out? I mean, like Oracle outside?
It can store to disk as well. Yeah, it handles storage as well, so it's persistent.
Store it, but would it operate on outside? I mean, can it operate outside the process? I mean, has it been loaded into the memory before you can do all this query?
So it's well, we do have out-of-core support.
Oh, okay.
So essentially, it doesn't have to be entirely in memory.
I mean, how's the performance then?
With out-of-core, the performance is not very good right now. It's in general, you want to have enough memory to hold whatever you're working on, or you're not going to get great performance. So we're kind of working on that, but out-of-core, it's kind of tricky to get it to really be fast. Yeah.
What sort of file formats? When you're reading from disk or persisting to disk, what sort of file formats do you support? I think you showed CSV, but do you guys have or plan to support like Parquet or like an HD5 or something not CSV?
Yeah, that's a good question. So right now we use basically CSV and our own binary format, which we use basically to make data M-mappable. So it's just a more efficient binary format that's really way more efficient. We are looking at using something like Parquet, which we think will have similar benefit but is more standard. Okay. So we're planning to probably add Parquet support and maybe some other things.
Cool.
Can you talk a little bit about like the memory format that's used by JuliaDB? Is it row-based, column-based, is customized format, or something more standard?
It's column-based, essentially.
But it's just a specific format to Julia.
It's not particularly weird. It's, so like if you have a array of random floating point numbers, it's just a floating point array like any other system. So it's not too strange. We will also do the standard tricks like specially storing arrays with few unique values, which are standard database kinds of techniques that Pandas also uses, where we will use some of those specialized column representations, compressed column representations as well. But it's nothing too exotic.
Yeah, got it. Thanks.
Is there any planned integration with Pandas directly? So like convert a JuliaDB table to a Pandas data frame or vice versa?
I think probably. I don't think it would be too hard to do because Julia Python interop is generally very good. So I think it would be quite possible to do that.
I think we can do it once the arrow format becomes a thing. We tried to do that actually a while ago, but there was like we felt like there was not enough support for user-defined types that we create in Julia that you want to also store in your data.
Yeah, that's also a really good point. Is that one thing about this is every Julia data type just automatically works. So you can define a new data type and it can store it immediately. And people have actually done this a lot. So there are a lot of interesting data types in Julia, like for currencies and dates of various sorts, and even things like colors and units, physical units on things, all kinds of exotic types like that, and it can just be handled natively with full performance. So if you have stuff like that in there, then it's difficult to transfer to like Pandas. But for standard data types, we could do it pretty easily.
You mentioned about units. Is there a way for you to specify the conversion of units? Like, we're not talking about USD versus pound, but say, for example, kilometers versus meter.
Yeah, so there's a units package that can do that. And you could store unit quantities in the database. And there's actually there's a neat currency types package in Julia that will do things like arithmetic, but if you add $1 plus £1, you get back out a currency basket that still has both because the exchange rate changes, so you can't just add them together. So there's actually a Julia package that does that, and you can use that with this.
So how would you compare like Julia's solution for ND sparse? I'm just interested particularly in arbitrary indexing. And using JuliaDB for that, which is my use case, versus like the Python alternative of doing it.
What Python
So
alternative?
I think it's like
Would you compare it to?
SciPy, which could
like the SciPy ND sparse. I guess the main difference is that it's distributed, built-in distributed, and I think it's much more flexible in what the indexes can be, because the index can be, in JuliaDB, can be any type that has a total order.
Okay, would you say like this is like a unique thing that JuliaDB offers? That
It's probably not globally unique, but it's slightly unusual, I guess.
Yeah. Okay, cool. Thanks.
Any other questions? Yeah.
Yeah, I'm pretty loud though. I can
Yeah.
Okay, I'll use it anyway. So you guys use Pandas as a comp. I've never actually dealt with storing data in Pandas unless I was pulling it back from a source. Wouldn't Spark be a better comp, and how do you guys comp to Spark?
Sure, we should do benchmarks against that as well.
Okay.
Yeah.
But I'm actually talking about the depth of the machine learning library. It's one of the problems you run into when you get into distributed attempts at coupling both languages together is usually your library of models diminishes pretty significantly because it's pretty difficult to apply those across multi-node problems. So how would you compare? I don't know how familiar you guys are with it, but like when it comes to the types of available ensemble models, like do you guys have a similar complement of neural networks, so on and so forth, random forests, the tree ensemblers that you'd see in, say, scikit-learn?
Okay. So yeah, machine learning. It's a good question. So I think this is, this whole area is a good example of why, in my view, you need a lot of generality, because what we've had in the past is somebody makes a big data system, but they weren't thinking about machine learning. The machine learning has to be done in some other language, and now you're faced with having to put them together, and it's annoying. So this is exactly where you need a system with more generality, in my view. And there are Julia machine learning packages. So we've done things like taking very large tables and using machine learning techniques on it in distributed memory, because it makes it easy to do that. I don't think we have an exactly comparable set of models as scikit-learn. I don't think we have as much at this point. But you could probably, if you really needed to, you could run Python inside of it, which would be a little bit defeat the purpose. But there are some really good Julia machine learning packages like KNet and Flux are the names of them. Is there anything else I should mention?
Mocha's a big one.
Mocha, there's Mocha. So these are really good machine learning frameworks.
So they'd be like the MLlib comps in Spark. So it'd be a good one to compare. Okay, because the only reason I'm asking is we use Spark, and that was one of the reasons. Check this out as a potential alternative. Spark itself has downfalls as well.
Yeah, so we have those packages exist in the Julia ecosystem, but I don't think it's the coverage is exactly the same.
Thanks.
Okay.
Yeah.
One more question.
Oh, what's the 1.0 story?
Really quickly, Julia 1.0 story is we have a feature freeze coming up on December 15th, and then that will basically be it. We will go through the normal release process. That will be 0.7, and then we will just remove all the things that were deprecated, and very shortly after that, we'll have 1.0. So we're very close.